much for the introduction and for having me here. Right. So the talk title is very long. I was hoping that the 30 minutes will be enough to fit the title at least, which it seems so. So, oh yeah, so this is all joint work with Luca Dallava, who's also here. So if you have any questions that are difficult, you can ask him. If you have easy questions, I'll take all of those.
So fair.
All right. So the talk will be about these triple product p-adic functions, and Alicia already gave a talk which sort of mentioned a lot of the ideas that wasn't in this talk as well. But I'll start with a recap of sort of the motivation for what we are trying to do in this work. So we'll start with three things: an elliptic curve over Q, and then two Artin representations, two-dimensional and odd. So there'll be some common splitting field H over Q, and this blended GL to L, and they're odd Artin reps. So that's sort of the three objects that we'll look at, and we'll look at this sort of part of the Mordell-Weil group where the Galois representation acts via this representation. So this is nicely encoded as this Hom space from ρ1 tends to ρ2 to EH, the Mordell-Weil group, and then you have the tensor of L, which is the coefficients of this representation. And this is supposed to be Galois equivariant, or Galois. Okay, so maybe the p-adic conjecture normally predicts that this group is related to some L function, this Mordell-Weil group. And there's sort of an equivariant version of this idea. So this is going to be p-adic, maybe an equivariant version. We'll say that this is related to an L function, which is the L function of the elliptic curve, sort of twisted by the Artin representation. And it's at S equals 1. So that there should be this connection to the L value. So for example, the order of vanishing of this should be equal to the rank of this group, and so on. So, so usually when one tries to study this problem, the convenient thing to do is sort of go to modular forms, and that's indeed why I put myself in this setup. So this elliptic curve will have a corresponding modular form of weight 2. And these two Artin representations will have modular forms G and H of weight 1. And the point is that the L function, which is normally difficult to study, can be studied as the L function of these three modular forms, F, G, and H, at S equals 1. And in fact, it can be studied very similarly to the way what was discussed in Ellen's talk. Really, there was this Rankins-Hellberg example with an Eisenstein series. If you replace that Eisenstein series with a Cusp form, you actually get these kinds of L values, depending on signs. I'll get to that in a second, but this really fits in this framework that Ellen talked about. Okay. So this is called a triple product L function. For obvious reasons, there's a product of three things. So that's the setup. And what is the actual goal? I don't know if this is a good board. Okay, I'll try. Okay, go. So the actual goal is to sort of study this p-adically, which is a fruitful method to study arithmetic of L functions. So study this p-adically. And more specifically, we want to give ourselves some room. So these three modular forms, we'll put them in p-adic families. So maybe I'm going to assume that P is a prime and F, G, H are ordinary at P. And now I'm going to consider Hida families through F So let's call them Fk, Gl, Hm. These are going to be the weights. And I'm going to assume some classicality hypothesis in the weight one forms, which I'll not say explicitly now, but I want this to specialize to the weight one forms or to p-stabilization of the weight one forms. Okay, I'm picking p-stabilizations along the way. Okay, so we deformed this in p-adic families. So these are sort of families through maybe p-stabilizations of FG. Okay. And instead of just considering this L value, we'll consider the central L value for these families. So, and consider this sort of p-adic variation where you take L Fk times GL times HM, and you evaluate it at the center of the functional equation, which in this case will be K plus L plus M minus 2 over 2. This is the center of the functional equation. Actually, maybe it's convenient to record the functional equation. So functional of this L function. So I'll just record an approximate version. So the functional equation will connect this value over here, HM at S, will be related to some epsilon factor and some other factors. So I'm writing a little twiddle because I don't want to focus too much on the other factors. There's some gamma factors as well, and so on. But there's an epsilon factor times, and then the same function. Okay, so okay, let me just simplify it to this. So K plus L plus M minus 2 minus S. So you see this point is exactly the center of that functional equation. And this epsilon factor is plus minus 1. And there's some other factors that I'm ignoring. So the typical thing that happens when you see this, if you plug in S to be the center, then like these two numbers become the same. And if you put epsilon equals minus 1, the two sides have to vanish. So in general, the way it works is that epsilon is minus 1, you have an odd order of vanishing. And if epsilon is plus 1, you have an even order of vanishing. So in other words, this Mordell-Weil group, it should be, or this Mordell-Weil group, it should be sort of odd or even ranked depending on this epsilon factor.
The question?
Yeah.
No, I think it was Alicia's talk. She imposed the condition that the central character of row 1 is the inverse. Make sure the L factors.
Yeah, I hesitated at some point to add this one. Let's add this hypothesis. So yeah, otherwise this won't actually be self-dual. So you would have some twist by a character on the other side, but I want to be that self-dual. Yeah, thanks for the question. Should have added that.
Can I ask a very naive question? Yeah. So why two art in representation and not just one?
Well, one can consider various variations of this. You could consider one, and then it would just be a rank in Selberg.
Yeah.
And that's a perfectly valid setting. I mean, and you can ask questions about like the L function of the elliptic curve twisted by one art in representation. And this is like some further generalization of that idea. Yeah.
In the rank in Selberg case, what you're about to say is known.
So yeah, so a lot of it should be known. So let me just think what the right. So definitely the construction of the p-adic L function would be due to Hida. And then this kind of, I mean, there's also this work of BDP, but I guess that's in the case where one of the forms is CM. Yeah, so I'm not sure, like maybe off the top of my head, I would have to remind myself also what happens in the general non-CM case. Definitely, like if you also assume that one of these things is CM, that would be work of Bertolini, Darmon, Prasanna. And then if you actually take some other exceptional, yeah, let me not answer this on the spot. Right? There's definitely a lot of work in that setting as well. So, okay, so this is sort of the setup. And now I want to so as I said, we sort of allow to vary these weights p-adically. And I want to draw sort of a picture of what the space of all the possible variations is. So I'm going to draw it like this. So there'll be four regions. Four. So the first region is where F dominates. So in this region, K is bigger than the sum of L plus M. So the F has the biggest weight, like sort of more than the sum of the other two. So for example, our point 211 is somewhere here, right? 1 plus 1 is 2. So yeah, 211 is somewhere here. And similarly, you can look at the region where G dominates. In other words, L is the biggest weight. And then you can have the region where H dominates. So M is the biggest of the weights, K plus L. And finally, you have this remaining region in the middle where none of the weights dominate, and this is called the balanced region. Now, so as I said, we allow ourselves to start from this point and sort of vary things in a p-adic family. So I can sort of go from here, and by varying the weights p-adically, leave my region where F dominates and go somewhere else. And the intuition is that every time you cross one of the boundaries, the epsilon factor changes. So the reason for this is that the epsilon factor is actually the product of the finite factors. So for v smaller than infinity, so v times epsilon infinity, and these stay the same, constant. And epsilon infinity changes as you go from a dominant region to a balanced region. Okay, so the epsilon factor sort of changes as you cross boundaries of this region. So now everything will depend on what epsilon factor we start with. So whether 211 has epsilon plus 1 or minus 1 will sort of determine what we want to do. I want to sort of section 2 of my talk, which is just going to be results. And I'll sort of simultaneously try to say what the results of the work of Darmon, Lauder, and Rocher are. So there's this work that Alicia also mentioned by Darmon, Lauder, and Rocher from 2015. And also in parallel try to say what we do with Luca. This is a preprint from this year. So, okay, so so I'm gonna drop sort of technical assumptions. Like some of these things might come with some level assumptions or something like that, and I'll let you maybe ask me or look at the papers. But it's like more or less gonna be true. So the key difference from the start is the assumption on this epsilon factor or on the rank. So they're going to assume that sort of the rank of this Mordell-Weil group, or maybe rather the order of vanishing of the L function, like this. So they start with a rank 2 situation. In other words, this epsilon factor, as I said, should start off as +1. And what we wanted to do in our work is to start with a rank 1 situation instead. 1. So in other words, for us, we start with an epsilon plus -1. And so Alicia talked about this assumption that epsilon is +1, and she mentioned also that it's sort of easy to satisfy. For example, if you assume that all the levels are co-prime, you'll satisfy it. This assumption is much harder to satisfy, and that's what will make our work also complicated, as I'll explain in a little bit. Okay, but it can be satisfied in many examples. So there'll be sort of there'll be 2 theorems and 1 conjecture. So let's say A theorem. So this one is actually due to maybe Darmon, Rocher, and Xie. Well, sort of first to Darmon, Rocher, and then also Xie. That there exists, so I should say what we're doing in terms of this picture. So we start with 2, 1, 1, and over there, the epsilon is +1. And so every time we cross a region, the epsilon factor changes. So if you start with, let me just do a full color. So if you start, let's say, with epsilon equals +1 over here, and you go into the balanced region, you'll end up with epsilon equals -1. So all the L values will vanish. And this is going to be bad for p-adic interpolation because you don't want to be interpolating a bunch of zeros. So you have to leave that region and go all the way to here, and your epsilon will be +1 again. And that's what they do. So what they do is they say there exists LPG, which is going to be a p-adic L function with G dominant. So let me call it G dominant p-adic L function. Sorry, I'm going to p-adic function with the following interpolation property. So if you take these weights LPG in the balance in the G dominant region, so let's say 2LM, or I could do it with K, but okay, let me just do 2LM. So L is bigger than 2 plus M. Then this is up to some factors like Euler factors at P and so on. This L value that we're interested in, L plus M over 2, divided by an appropriate period, and this number will be algebraic, and the algebraicity is due to Harrison Kudla. I'll preempt that question again. Okay, so this is what the interpolation property looks like. And we sort of do something similar in this case. So the first theorem is as well. Okay, so now I should say the difference is that we start with epsilon equals -1, right? So if you start with epsilon equals -1, and you go into this region, it becomes +1 already. So we don't want to go all the way to the dominance region. We want to stay in the balanced region, and then we have a chance for sort of non-vanishing of these things. So our theorem is that there exists LP bal, which is a balanced p-adic L function. Such that LP bal, I missed, it's sort of like a square root p-adic L function. There's actually a square over there. Well, it depends how you define it, but the way I'm doing it is the square of that L function is the L value. So this is, again, the appropriate L value. Let me just write it like this. So one way to easily put yourself in the balanced region is you could take the weight here 2LL, or L bigger equal than 3, then definitely nothing dominates. And here you could put yourself in this region by taking 2LN for L bigger than +N. So this is like the simplest way to do it. So let me do it like this. And then the center is out. And what you divide by is just the 3 Peterson norms. So it's a bit different. The L function is balanced, and sort of the period is also balanced. This one, and then HL. And you could allow more general variations of the weights, but I'm just simplifying that. So this is for, I guess, L bigger equal than 2. Oh, I could have done.
Just going to break down due to Greenberg and Sabeza.
Yeah, so sorry, I'm just let me just like finish writing. Sorry, so okay, so there's this theorem, and so I'm gonna say like extending, and I'll say in a second what we're really extending. So Greenberg, that's it. So, and then also Shia. So I'll say like, so under the particular assumptions that I put myself under, their theorems just don't apply, and we have to sort of do some work to overcome those difficulties. So I'll get to that in just a second after I state.
Just one second, because you said something about the epsilon factor. So epsilon infinity is one in the middle region.
So epsilon infinity is, wait, so it's how does it work? So epsilon infinity is like +1 here and -1 here.
Yeah. So I'm a little bit confused by your remark that it's much more difficult the other region, because I mean the epsilon infinity changes, but you also change you require some different factor globally, so like you still, the epsilon finite is always one for you, right?
Sorry, no, I did this the opposite. In this region. Yeah, so epsilon infinite, no, this is correct, right? So if I want epsilon to be -1 in the dominant region, I need there exists some v finite such that epsilon v is -1.
That's difficult, definitely.
That's what's difficult. to say.
That's also the case in on the left board.
No, so here they actually assume epsilon v is +1 for all v. So that's it. That's one of that.
You said that epsilon, the sign is -1 then? I don't get it.
No, so epsilon infinity is +1.
The global sign in the middle, if epsilon v is one for all v,
So, am I doing this the opposite?
I think it's right as written.
if epsilon v is one for all finite v, and epsilon infinity is -1, in the balanced region, you'll have global sign -1.
But they are interpolating in the G dominant region. They're interpolating over here where epsilon infinity is +1.
Which is fine, okay.
Yeah. So that's why. So indeed, if they went to the balanced region, they would get 0. But they go all the way like over here where they get non-vanishing.
Okay, it's clear now.
Right. So anyway, yeah. So just to be clear, like this construction is due to Greenberg's assignments, yeah. But there's some ramification assumptions that cause problems that we're solving. And then okay, so this is like, I just don't want to call this A, sorry. I want to call, like, I want to go like vertically down and call things B and C. So, okay, so at this point, I also, okay, so let me just finish stating the results. So there's going to be results B and C. So sorry, B is going to be a conjecture due to, again, Darmon, Lauder, and Rothschild. And this is the conjecture that Alicia mentioned in her talk, which is that if you go back to the value at 211, so you sort of interpolate in the other region, but go back to the first region, this should be related up to some rational factor to this 2x2 regulator. So there's 2x2 matrix of sort of log p-adic with formal group law, logs of points on the curve, J. And in the denominator, there'll be a p-adic log of a certain Stark unit associated to G. So UG is an OH cross, and it's in the add row G isotypic component. And these Pij are in this Mordell-Weil group tensor L. So again, in the correct isotypic component. But yeah. Okay. So there's somehow, so this is their conjecture that this is related to that. And then they proved it. So again, DLR. So true when at G and H or CM have CM for, so CM by the same imaginary quadratic field. So if there are theta series associated to the same imaginary quadratic field, plus some ramification assumptions, they prove that expectation based on some factorization of the p-adic L function. And so similarly, for us, we make a conjecture. So that conjecture is about the value of this balanced p-adic L function at 211. And so here there's just one point. So P should be this point in EH and for L. But in the denominator, we're sort of, G and H are now playing the same role. And for that reason, there should be both the log UG, log UH. But there should be some sort of square root of these. So similarly to the way this was a square and those were not squares, similarly here we're getting square roots. Okay, and this UG, UH are again in like OH cross tensor L. And And then finally C, true in the same CM case. Or, which is again based off of some factorization, and this is a Higner point, and these are these Stark these these units in imaginary quadratic field. And then I should give a remark that there is this forthcoming work of Andrietta, Bertolini, Savessa, and Benucci, who give a different construction. So gives a different construction of the balanced p-adic function, or something close to it anyway, using Yoshida lifts to Ziegel modular varieties. So using sort of a different group and a different integral representation. And they sort of study this point, study 211 as well. So going back to 211, and they even construct some Selmer classes or something like that. So it's forthcoming work. So maybe I'll I'll just say this is like what they announced they're doing. Okay, so this is the summary of the sort of results, or the two theorems and the conjecture, and in the two cases. So any questions at this point? Yeah.
Can you view this conjecture B? Can you turn it into a construction of a global point?
Yeah, you could do like X, P, P. Yeah, exactly. In new cases, you could do that this value, whatever this analytic function evaluated here times the two logs, should be a global point on the elliptic curve. So that is kind of nice, because this construction doesn't easily turn into constructions of points because there's this 2x2 regulator. But because we're in the rank 1 setting, you do get this sort of construction of a point using this p-adic method.
Would you be able to make that explicit?
I mean, it says well, I don't know. It says explicit as like the value of this p-adic function. Okay, maybe we can talk about it after, but it's sort of explicit, but also complicated.
Can you do now in numerical calculations and see that it's actually?
Yeah, so beyond the CM case, that's something that maybe we would like to do, but isn't yet done. It's not so easy to compute these values in practice. Any other questions at this point? I'm trying to remember how much time I have.
3 minutes?
Okay, cool. So let me now just try to mention what the key difficulty is that we're trying to solve. Over here. So, okay. So the key technical difficulty, and the reason that these other works don't really apply to what we would like to do, is to guarantee that this epsilon factor is -1. So, the point is that remember that there's this product of finite factors times the epsilon factor at infinity, which should be equal to -1. And as I said, this epsilon infinity is +1. So there is some v such that epsilon v is -1. So some finite prime. And so because f, g, and h are classical, especially g and h are classical, you can't have, at the finite places, you can't have twists of Steinberg. So actually to guarantee this, you have to assume sort of that at least g and h are supercuspidal at b of level, well, so we're going to assume they're actually of level b squared. Or like b squared at v at least. That's the simplest case. And now, right, so that's that's the issue, because now now the integral representation will happen on a definite quaternion algebra, which is ramified exactly at those same primes, at v smaller than infinity, such that this epsilon v is -1. So these epsilon factors dictate where the quaternion algebra is ramified. That gives you the integral representation for the L function. So HM. So it's C for the center. It's going to be roughly an integral on this quaternion algebra of some Jacques-Lang transfers of the forms. That's GL times HM, where these are Jacques-Lang transfers of FGH. But you see, if you want to transfer something of level v squared, and the quaternion algebra is ramified at that place, you have to go to these strange level structures at v. So these are not either orders at v, is the point. And so there's this observation due to Heiser that in this setting, let me just write it briefly since I'm running out of time. So for example, if you look at this space of quaternionic modular forms of the correct level, like let's say ng times v, well, some n times v squared, where is the level, and then I look at the g isotopic component, and v is supercuspidal, sorry, GL is supercuspidal at v, this will actually be two-dimensional. And so this kind of thing is prohibited by the assumptions of, let's say, Greenberg, Savessa, or Shea. So the point is, like, this Jacques-Lang transfer, there's really two choices of forms that you can make on this quaternionic side, and it's not clear how to make them, and it's not clear how to do it across a family, for example. So we need to do it across a whole Hida family or some piece of it, and that seems difficult. So let me just mention in the last thing I'll say is sort of how we resolve this issue. So we define an extra operator, sort of not like it's sort of some Heck operator on the quaternion algebra, but it's not one of the classical ones. So extra operator. It comes from the uniformizer of the quaternion algebra at V. I'm going to call it pi V, such that if I look at this space, NV squared GL, so I look at this Hecke isotopic component, but I also look at the part where this extra operator acts as plus or minus one, then both these spaces are actually one-dimensional. Okay. So even though this is two-dimensional, there is some extra operator which recovers this one-dimensionality of eigenspaces. And then we can sort of, then we have to do quite a bit of work to transfer. So when I said these should be transfers, now we want to transfer like whole Hida families, and we can do it for either choice of sign. And then for either choice of sign, we compute some local factors. And it turns out to be quite important that you have this flexibility. So if you just choose random forms in here in this two-dimensional eigenspace, sometimes this integral may end up being zero. It's really not trivial to conclude that. Okay, so this is the key result that makes our construction work.